Okay, hey everybody, welcome back. This is another Kevin and Zach live stream. We're going to do some live coding again for you. Last week, we actually brought to you two different episodes where we solved a problem from Rosetta Code, and then later that week, we wrote a function with some members of the Wolfram function repository team to eventually submit to the repository, just as an example of how that would go. This week, we're bringing it back to the old classic. We're going to try some Rosetta Code problems. It looks like a lot of the problems have been being solved in Mathematica, so if we start hitting some ones that aren't super interesting, I've found a few that might be more interesting for us to look at, and we'll just transition over to those if need be. Um, Again, I've got with me here today, Zach.
Hello, everyone. Welcome back. Very excited to get started.
Very excited. Let's do it. Let's just dive right in. So I'm gonna start sharing my screen here. All righty. So we've got the typical web scraping here going on where we're going to take the tasks not implemented in Mathematica from Rosetta Code, get them into a nice little list of URLs, collapse that for visibility. And let's just see how many of those we've still got remaining. Look at that, 202. I think earlier today it was like 205. So you guys are solving these like crazy. That's great. We started at around 329, I think. So over 100 of those gone. Fantastic. Okay, the one that came up first is, oh, cool. Okay, I've
we
heard
we were
of
talking about this before.
yeah, four is magic. That's a classic like word game type of thing, right? Have you heard of this, Zach?
I've heard of this. We did it in like maybe like I think we did it in like a C++ class once when I was a
Uh-huh.
freshman in college.
Yeah, I think the whole basis is that the only number whose the number of characters in the word representation is equal to the number itself is 4. So 4 has 4 letters. I guess this is kind of giving away the problem for anyone who's never seen this before, but we have to do it to solve it. So yeah, like 3 has 5 letters, so it's not magic as they call it, as this calls it. I've heard it referred to as cosmic or other things. But yeah, 4 has 4 letters, so it's magic. It has the same number of letters as itself.
So
Right off the
we
bat,
Yeah.
yeah,
Can we use, isn't there a function to pull up just like the word form of a
right.
number, of any number, I should say?
Yeah. Let's see. Number to word. I forget what it's called, but
I can
let's.
remember it either.
Oh, wait. Well, it has to be an integer. So,
It's like integer word or something.
mm,
Oh, we're just Um, I'll
it's gonna be
find
in
it.
here somewhere. Oh, random word. That's cool. Let's see. Probably in here somewhere.
Integer name, I think is what
Oh,
it
integer
is.
name. Is that it? That
Yes.
makes sense. Cool, aptly named function. Yeah, it was right there on the bottom of my screen right before I clicked away. So gives a string containing the full English name of the integer n. So for example, the integer name of 4 is, as we saw earlier, oh, starting at my kernel. And that'll only happen the first time. It just has to input all that data, and we get 4. Run
Wow.
that again, it's super quick. So yep, example 67. Now, I do remember I've seen this before. Yeah, so sometimes it uses numbers and words for this function, but for the 4 is magic type of thing, let me just pull this over so we can see. It looks like they only want us to use words, right? Like, oh, here, big number is just 20,140. So I think there's a way to get that using an option. Yep,
We
words
want
only.
words only. Okay.
Yeah. So we have some different options, different qualifiers, they call them. The automatic is just, it chooses based on the input. It, and that's Mathematica doing most of the work for you. That's great. But you can specify it more specifically. You can get some approximate words. Cool. So let me just set up the section header. This is 4 is magic. And let's see, the first thing we do is take the integer name of some integer. Look at that, it's 4. And we want to see that the string length for, let me wrap that in a different way. So this is the same way to apply a function. And we want to make sure that that's equal to the number itself. So true for 4 isn't true for any other number, is at least what the problem assumes. Cool. There's a lot of guidelines and whatever here, but I'm just going to assume that we're trying to make this output for basically any number. That sounds way more fun, right?
Yeah.
Than whatever they're doing with all
It
those
seems it
words.
seems like they just want there's a lot of like stipulations, and one of them's like your numbers, if you're printing out a number, it should have commas.
Yeah.
You know, they're
Oh,
not
okay.
looking for the most complicated solution. Um, they're just looking for a solution. We can try to support negative numbers.
Yeah.
We want to have, we can have capitalization if we believe in grammar. Um,
Mm-hmm.
and
Oh, looks like we already support negative numbers, so
there
that's
you
built
go.
in for us.
There you go.
So the first thing that I notice is for the structure of this code, you're going to be running down through some numbers until you hit a condition whereby the length of the name of that number is equal to the number itself. So that's going to by default be some sort of while loop. You're doing something while the length isn't equal to the number. When it is, you're done. The question then is what kind of while loop? I immediately go to a nest while list, mostly because this is kind of in the form of a list. It might not look like that, but you've basically got a list here, 0, 4, 1, 3, 5, 4. Then the rest is just string formatting. So once you've built that list, you'll add in the words is, whatever. But yeah, we're just trying to generate this list first off of 3, 5, 4, etc. And we'll build in the rest of it. Okay. And so that's why I wanted list. And the reason I wanted nest is because each input to the while is going to require the previous one. And that's what a nested structure is. So you start with 1 and that gives you 3. Then you use 3 to get 5. Then you use 5 to get 4. And so that's that kind of nested structure there, as opposed to, say, incrementing from 1, 2, 3, 4, 5. You're using the previous value to calculate the next. Not like a recurrence. Whoops. Get this.
Okay.
I'll make that big. All right,
So
so nest while list. Question is, what's our function? And I think the function is just the string length of of the name of a number. Oh, and as we'd said, we wanted words here. Yeah, so this would be important for something big. Oh, okay, yeah, using string length there, but cool. 2000. Oh, it said we don't want commas. Is that
so
right,
you
Zach?
should use cardinal form. Cardinal
Ah,
form is if you use cardinal form, you'll get no commas.
okay. Is that? Oh, cool. So that's what they said in here. You should use cardinal form.
Yeah,
I see.
it's just the no. It's just the no, what's it called? But basically, it's if you have like a number, it'll always be like 45 hyphen.
Yeah.
So
Oh, cool. Perfect. Okay, great. So it's great that that's built in. We can just say cardinal, just like they wanted, and there we have it. All right. So what we're doing is we're creating a function that gives the length of the name of a number in cardinal form. We apply it to some input value. What's one of the inputs they start with? Maybe 1 gives us a nice one. So 1 should be 1, 3, 5, 4. So we'll apply this to 1. And the test is while, let's see, while while the number is not equal to its length, the length of that string, right? Yeah.
yeah, so it'd be the integer name if that, yeah, I guess it's equal to itself.
Mm-hmm.
Well,
So
now I guess hopefully we don't
not
find a
equal.
number that isn't equal to itself. I don't know if there's another I guess if we find it, it's another magic number. So, oh,
Is
okay.
that what we expected? 1, 3, 5, 4. So 1 is 3 because it has 3 letters, O-N-E. 3 has 5 letters, T-H-R-E-E. 5 has 4 letters, F-I-V-E. And 4 is magic. So there we
Wow.
did it. And we could do this for any of those, like 0 gives 4, 4 is magic. Um, 2 is 3, 3 is 5, 5 is 4, 3 is 5, etc. Now, this would be possibly easier to do recursively because you would be every time that you have 5, 5 always goes to 4, right? And so once you can have that done once and save it, you're
Mm-hmm.
kind of golden. You've memoized the code. Um, but I think we're fine using it the way we are, where you basically redo it every time because you're not going to go through this list a ton of times, and it doesn't seem to take a ton of time to get the integer name. So, yep, 9 is 4, just like they said. Great. So, all right, basically all we have left is just getting this into this format. Um, one thing that we could do is try to get all of these into integer names, right? Because it looks like it needs to be 9 for the actual word. So that's just this function that we already used. Here, I'm gonna and apply this to every element in it by mapping across it. So we change 9, 4 to 9, comma 4. Cool,
Well,
cool.
we wanna write like 4 is magic, 5 is magic. So,
Hmm.
okay.
Only 4 is magic.
Okay,
5 is 4.
so I guess that's true. Yeah, right. So you wanna do outside this nest while loop?
Well, we've got the results here. We just got to get it into string format, right?
Okay. Yeah, that's
Yeah.
I guess my idea is like, what do you normally if you were doing this, in like say Python, you would just have an outer for loop where you're just run or a while loop and you're like
Hmm.
while, string length is not integer or equal to integer name or the number. Um, you would just say then this number is the next number and you would print that each time programmatically.
Right. Yeah. Yeah, I guess this is just a slightly different approach where we generate the list and then
Mhm.
convert it.
Okay.
Yeah, we could try that after this too. So I'm
I
thinking I remember some function that will change the delimiter in a list to anything in a string. So we could change all these commas to is blank. I'm also noticing something else. The way that this is formatted, right? It's got 1 is 3 and then 3 is 5. So we want, uh,
So you wanna isn't that make the pairs, right? There's a
yeah, we
way to
need to kind
like,
of partition this, right?
yeah, make the partitions. I
Yeah,
don't now when you do partition, it doesn't just there's a way to indicate that you want to partition to like pairs of two and you would double,
right.
you would essentially double your three and your five.
Yep. Yeah, and I think that's using this offset here. And
Fixed
so
point list. Okay. There's a recommendation to use fixed point list.
fixed point list.
I've never used it, so I'll look into it. You keep working with this and
Okay, yeah, go
finish
ahead and look
this,
at
and
fixed point list.
I'll look at this.
Um, and so in the meantime, yeah, we've partitioned this. So partition into groups of 2 using an offset of 1, means that each one is repeated once. So now we have 1 is 3, 3 is 5, 5 is 4, etc. Okay, great. So now we want to group these into, uh, we want to change these commas into the word is pretty much. So 1 is 3. And oh, there's a way to do that. Like string delimiter, maybe? Delimiter. Hmm.
You could also use string join too.
Oh, yeah.
Yeah, you just write like a string join pure function.
Oh,
It's
yeah,
the two
yeah, yeah.
carets next to each other, yeah.
And is there a way?
You could also flatten it too. So you could
Mhm.
flatten your list and then join it. So then you would have 1 is 3, 3 is 5, or you would have 1, 3, joined together basically. Ah, okay.
So I think this is kind of what you're going for. Some function
String
that,
riffle.
oh, string riffle. Ooh, fancy. Okay, that's probably what I was thinking of.
So
Maybe.
what is riffle? Riffle is
Oh,
just you're putting them together. Okay, so this just does all the work that I was trying to do with multiple functions. I
yeah,
see. Very cool. That's convenient. Hmm.
perfect. So yeah, it takes a list of 1, 5 and replaces it with
And you
with a
can,
space.
and it looks like you put a separator in, so you could say, is whatever.
Yeah, 1 is 5. Perfect. That's exactly what we want.
And then at
Great.
the end, you could just say, and then at the end, you always append 4 is magic.
Yeah, exactly. Yep. Yeah, so that would be probably the only thing we're missing so far. Um, okay, so we've got this, and we want to map this across it. Great, so we've riffled all of these inner ones. So now we got 1 is 3, 3 is 5, 5 is 4. Great. And then we would need to add exactly like you said, 4 is magic. So we'll add that as a part of the list. So we need to add an element to a list. We could use append, we could use join. I'm going to use join in this case. I'm not super sure why. Yeah, I'm not super sure why, but let's do it. So we've got some list and we want to join it to 4 is magic. And this is to be a list itself. Cool. All right, 4 is magic, just like that. All right, so we've got it almost in the right spot. 1 is 3, 3 is 5, 5 is 4, 4 is magic. We just need to replace all these commas with spaces, which is exactly that string riffle function that we just looked at. Yeah, we actually literally just need to apply string riffle to this. Oh, with commas instead of spaces, right? So we need to use the delimiter comma space instead of just space. Cool, so I threw that comment in there, and now we've got 1 is 3, 3 is 5, 5 is 4, 4 is magic. Pretty neat. Oh, I'll just add a period, not that that's a super big deal. But
Mm,
yeah,
okay. All right. So looking at oh, Brian was saying that string riffle can do different separators at different levels.
oh, okay. So
So
instead of what I did where I mapped it and then later applied it, we could have just done it. Oh, cool. So string riffle with separator 1, separator 2 inserts the separators between elements of list at different levels, 1 and 2. That's pretty neat. So yeah, basically we could clean this up. Yeah, we could clean this up. Let's see, how would we do that? What we want, let's go back a few steps to kind of tough one is 4 is magic, but I guess we could always add that later. Yeah, we could always just add that later. So why don't we go back to this step where we had 1, 3, 3, 5, 5, 4, and we're going to use different delimiters on this string riffle. String riffle on the first level first level, we want it to be comma space. And on the second level, we want it to be is, I think. I might be wrong in the ordering there. We'll see if this works. 1 is 3, 3 is 5, 5 is 4. And then we just need to add this. 1 is 3, 3 is 5, 5 is 4, 4 is magic. Awesome. Yeah, so thanks to Brian, that definitely cleaned it up a lot. So we're just using string riffle once instead of applying it and mapping it and doing a bunch of crazy stuff that I was doing before.
So you
Now,
join. So you just string join. I get it.
oh, yeah,
Okay.
yeah. I should probably explain. This is a shorthand for string join, which makes your code look a lot neater. So instead of saying something like string join of hi, which works, you can just say hi joined with Kevin. And that's doing the same exact thing, joining two strings. So it, it just kind of looks nicer to have this join in that shorthand notation. Yeah.
So someone asked, and you might want to hop over to the Rosetta code, but he asked why we
Hmm.
don't just test for the number being 4. And I guess the reason that is because we're looking for, this is all about like 4 is the magic number, but the reason 4 is magic is because it's the same number of letters as it
Hmm.
is its number. So theoretically, we could find another number in, Oblivion, or probably not. There probably isn't another magic number. That's the point. But, you know, that's the reason 4 is magic. But we could also just test, you know,
Right.
whatever. Try, we want to test this with 100, and then once you're done, I remade this function with the fixed point list instead.
Oh, cool. Yeah, we'll look at that
I'll,
next.
I'll send that
Yeah,
over
so
to
I
you.
guess the reason we don't just test that the number is 4 is because that's using the knowledge that 4 is magic, but we're basically here confirming that 4 is magic. Magic meaning that it has the same number of letters in its word representation as itself. 4 has 4 letters. Um, so it might be slightly quicker to test that it's 4 computationally, but you're kind of assuming the answer then, and it would still work. So
So,
here it is with 100, a little bit more steps. 100 is 11, 11 is 6, 6 is 3, etc. We can even go pretty big here. 2 billion. Whoa.
very big number. It's
Very,
103. 103 is 17, and 17 is 9, and 9 is
right.
4. 4 is magic. I just sent you the fixed point iterator that you
Mm-hmm.
could look at. So how this works is it's similar to the while loop, but
Okay.
instead of ending at a condition that we create, it ends when it stops, when it repeats itself. So if you remove the -2 and you just print out the whole list,
Right.
you'll see that it prints 4 twice because it repeats.
Okay.
So it just stops when it repeats itself.
Okay. And so all this is doing is just
Yeah,
getting rid of the last element,
yeah,
right?
there might be
Mm-hmm.
a better way to do it, but
Yeah,
I was
one
like,
way we could do it is just say drop I think -1.
there you
Yeah,
go.
so this just drops the last element. They both do the same thing, but
And and then you can just plug it back in and you'll get that whatever.
oh, Dylan says, aren't we assuming the answer by hard coding the word for at the end? That, yeah, that's a really
We
good point. Of course we
we
are.
are assuming that it is 4. We are assuming that we get to 4 is magic. Yes, that
Yeah,
is true. But we could make this print this out as instead, if you want to string join instead, you could just string join the last like value in the list.
right.
Which write that out. Let's do it right so if we can assume.
Yeah.
So we instead of joining the comma 4 is magic, we just join like the last number in the list. That is
Right.
magic.
Yeah.
It's a very good point, Dylan. We should code like we're not assuming.
Yeah. So we'll go back in here. So we want this 4 to come from the list itself. Let's go back to an easier number like 1. Um, and in fact, I'm just going to go back and look at
Are you gonna
list
name this?
itself.
You wanna? Could we use the with? You notice with being used sometimes, and I assume that's when you just name it in the function so that you can call it later.
Yeah, for example, we could say with n equals 1, and instead of saying 1 here, call this n.
Oh, okay.
Yeah, so using that as a local variable, and then later we'll be able to go in here and it's more obvious what you need to change. Yeah, that's a good point.
I see. Okay, well, I was just curious. Could
Yeah.
we could we use so how would we recall this, this list we made, right?
Recall it.
Well, we need to recall it to join the string, right? To join the last number.
Oh, mhm. Right. Yeah, so we want the 4 to kind of come at the end, so we can say 4 is magic.
Well, we could if what you could do is you could use fixed point list and then drop and then get rid of dropping the last one. And then we would have an errand like a second 4.
Oh, right, right.
Since it prints 4 twice.
Mm-hmm.
So you could just do fixed point list instead of nested while list, and it would get exactly what we wanted.
Something that I thought of, and I just want to try this quick is, well, so we've got this in the format of 5 is 4, and the last one should be 4 is magic. So if we just have the last element of this list, or sorry, if we have the last element, meaning that I want to join it, fancy way to do join, right? No, not really.
You just
I can do it this
just
way.
just join. Yeah,
Yeah,
you do the
this is
infix.
infix. Yep, good. Um, I join that with the word magic. Um,
Since it's because it's a nested while list, so when you join it, it's gonna apply it to it's gonna put it in your function, right?
yeah,
Assuming.
I didn't want to convert it to an integer name, so I should have used parentheses to show the order there.
Oh,
So 1 is 3, 3 is 5, 5 is 4, 4 is magic.
there you
And
go.
then we would just get this in the format using string riffle. So we'll get string riffle back in the business where we riffled it out with all these delimiters. Cool.
Wow.
All right, so now we're not assuming. Thanks for that catch there, Dylan. That was a great point. Yeah, if for some reason the last fixed point was 7, even though we know that's not possible, then it would print 7 as magic.
So you're just joining inside of the list created you just made.
Yeah,
Ah, okay. That's really cool.
and this has another advantage of when we put 4 in here, it actually says 4 is magic. Previously, I don't know if you noticed, but since we were joining comma 4 is magic, the last thing was comma 4 is magic if you put in 4, which wasn't correct technically. But this looks
Oh,
better. Also just going to join a period at the end. Not that it super matters. We could also try to capitalize its first letter. You see here they have the first letter of all theirs capitalized.
oh, how good. We
Is
how we just
uppercase?
two uppercase the first one.
Yeah. So this would yield a string in which all letters have been converted to uppercase. Um, let's see. I guess we could just do that to the first letter, right? You need examples that show us what we want. No. I was thinking there was a way to just convert the first letter to uppercase. But we can just use this function. So let's see, how do we apply something to just the first element of a string?
Um, I don't know. I'm not actually sure. Wouldn't it just be first? Wouldn't you just call first and then just make it capital?
Right, but if we do first, we lose the rest of it, right?
I would we? I don't think we would.
Or, oh, first of a list isn't happy. I think our list's atomic. Or sorry,
Uh,
strings, I should say. Strings
I
atomic?
think strings are
Yes,
atomic.
strings are atomic. Um, Something we could try is something suggested in the chat of using map at. Um, but I think we still have the issue of strings being atomic, so we can't index into them.
Well, can't you just two uppercase the string?
Yeah, we could do the whole string,
I
but
mean,
do we
wouldn't
want
you
to be
be able?
yelling?
Okay, what if you, what if you, there's, all right, I'm just gonna say there's probably a string function that like capitalizes the first letter.
Right.
I feel like this is an issue that a lot of people probably faced, and I think we've probably come up with a solution to this. Even we could look at it, there's a capitalize function.
Ah, there's a capitalized function. There we go. That's what I was looking for.
This
Okay,
might be
perfect.
slow, but I have no idea. It probably is just enough. Good
I'd
enough.
imagine it's pretty quick.
I assume. It
Yeah,
probably did. It probably, converts the
let's
characters and
decide
then
the width.
so you would when you map at, right? Or are you capitalizing them all?
Well, I think the way capitalize works is it yields a string, just the first character has been made uppercase.
Yeah, yeah. So will it do that to all of them? Would that be incorrect if all of them are capitalized?
Well, I think it looks here like just the first letter of the whole sentence is capitalized
Okay,
in this
since we
format. So,
string riffled it, we made it one string. Never mind. I
yeah.
understand.
Oh, right, right. Yeah, this is just one string. So when we do it, we're just
I get it.
capitalizing the first letter of the whole string. So if we
I
went back
see.
to one, we get exactly the output that they were looking for in the problem.
There you go.
Pretty neat. One is three. Yeah. Okay. We can turn this into kind of a function. So we call it, I don't know, just magic maybe. Not super descriptive, but
It's fine. Whoa, the
uh,
N is red. Why is that? Oh, that's
oh
why.
yeah, I had two definitions for n there. I was using the previous one inside the with statement.
Does
Now
not
I'm
like that.
using, yeah, now I'm using it as a function definition. So anytime n is seen, it replaces it with the input to the function. The only time it shows up is way down here. And that's telling it what the first letter should be. So magic of one gives us that string. Sweet.
Wow. Okay, cool.
It's a big
All right.
number. Cool. Four is
Anything
magic.
e- anything else to do?
Let's go look back at that fixed point that you were talking about. I'm just gonna copy it again. So this is what Zach had written out.
This was a recommendation from a viewer that
Oh,
I
this
will
is pretty neat.
reference. It was
Okay.
from Brian who recommended. Wait, was it? Yeah, it was Brian. Thank you, Brian.
Yeah. So what's
Integer
going on
name.
here is, oh yeah.
With integer name number, Cn equals integer name number cardinal n.
Let me go back here. Yeah, we're getting the good suggestion that we should just find some function to be this guy since it's used all the time. Um, yeah, we want that, right? The only thing I'm slightly, this will work. The only thing I'm
Maybe
worried about is when we have to use it inside of string length. Um,
using a rule. Using a rule
This will
to
still
handle a
work.
magic. String riffle, fixed point, string length, integer name
This
100, cardinal
this
2,
will still work.
1. Oh my gosh.
Will this still work?
This looks very clever. I'm gonna let Kevin look at this, Brian. When you get the
And,
chance, you should look at this because
oh,
this might be over. There's a lot of infix and inline stuff.
uh,
It's definitely a bit
yes. So the
a wee
proper way
bit
to
over my
get
head at the
this
moment.
is using the, and what's going on here, going to go to the documentation for composition. So we're actually composing these functions to create a new function. Um, so if we just wrote out f of g, it's not a pure function and it wouldn't really know how to use it. But using this composition, we can symbolically define some function that is f of g of h that can then later be applied to an input. So this is great. We want this exact same thing right here. And now we should have a function that works without having to redefine this integer name a bajillion times in there. Okay, great. Yes, this is a little bit cleaner. All right, is this what you were talking about, Zach? This guy here?
Yes, yes. I don't know what the colon arrow means, and I just thought that was an interesting way of
This?
doing it.
Yeah, so that is a delayed rule, I believe. Let's see. And what it means is a rule delayed, sorry. So instead of a rule meaning like a with a going to 5, say we wanted a to go to the current time. We want that to be evaluated later when the replacement actually happens. So this now isn't evaluated until this rule is actually looked up. So if I were to do this now, the time would actually change. So that's good. That's what this rule delayed is. Evaluates the right hand side only after the rule is used. Cool. So what we've got going on here is the same string riffle we used, same partition. Oh, okay. And if it sees two numbers that are the same, meaning a fixed point, which is only for 4, then it replaces it with 4 and magic. Pretty neat.
So if it gets a fixed point, then it just says, oh, so yeah, if it gets the same number in the last one, it just, okay,
Yeah.
cool.
Yeah, so this fixed point list thing is pretty neat. Let's look at what it's actually generating here. Oh, that's the partition. Cool. So yeah, we're creating fixed points of integer names that have sorry, we're repeatedly finding the next integer name based off of the last integer name's length until there's a fixed point. So we don't even have to do up here in the while loop where we're waiting until the length was, where's my while loop? Oh, this isn't the while loop. Yeah, in the while loop, we were waiting until the length was equal to itself. Now we don't even have to do that because that's what fixed point's looking for. It's looking for something is equal to itself. So this is a fixed point of the length of the integer name. Sweet.
So it's a fixed point, integer name, and it does, okay. So do we got a lot of different ways to do it. We could we tried doing an absolute timing test with like a very big number just to
True.
look and see what's going on.
Yeah. Let's call this maybe magic 2. Um, none for clarity's sake, and the none goes in right here. That's the input. So let's just confirm that they give us the same result. Ooh, oh, let's see what we got. We saw. Did that not work there? Magic of 100. 100 is
Oh,
magic. Oh, I must have changed something. Hold on. That's not right. 100 is not magic. Um, this is where I last defined magic. It's not good because 100 is most definitely not magic. Ah, okay. Luckily, someone caught this. I didn't. Um, yeah, when I went and used this composition here, I actually messed up the condition on the while loop, and it looks like it was probably just always evaluating to, yeah, that's true. So what we've got here now is that the string length of the integer name in the cardinal is not equal to itself. What I had before was moderately nonsensical. So this should
Oh,
be the appropriate definition for magic. And let's just confirm that. Ooh,
okay.
two. Cool. Oh, but without the period. So we'll need to just add the period. Not a big deal. And now these two should be the same. Oh, up to the capitalization. Capitalize. This is just other stuff that we added to our magic one function. Well, magic. Great. Now they look identical. And we'll confirm that the two outputs, output 86 and output 87, are the same. Good. Okay. Now we have defined the same function, doing the exact same thing. And you said you wanted to see which one's quicker, right, Zach?
I mean, yeah, it'd be an interesting test, you know.
Yeah. So we'll
It
do.
looks like I was doing some testing. It looks like at like a certain threshold, cardinal does not is not able to convert our numbers into integer
Oh,
names.
oh, at
It
really big
will,
numbers?
yeah, we'll see what we do, what happens. But if you take like I took a number like 10 to the 20th or something, and I was like, no, does not compute.
Yeah. Too
So
large. Hmm.
so
Okay. I suppose that's somewhat reasonable. I imagine if
Dylan,
you were to write this out in cardinal form, what do we have? Thousand, million, billion, trillion, etc. You know?
a lot of numbers.
Yeah.
We
See
won't
if
want to
that's
go that high.
documented. For very large integers, only approximate and approximate words are supported. That makes sense.
What's approximate words per out? Just
So
out of curiosity.
it says it does the first few digits or the first few digits as words,
Oh, okay.
and then
So
thousands,
it'll
millions. So it's not great. Like if we did this one, 1 million, etc. If we did that as approximate words, I think it would just say like 1 million. Yeah.
1 million. Ah, that's close enough. 1 million.
Right. It makes sense for these really big numbers. You've got whoa, billion, billion. Yeah.
Ah, a billion billion. Okay, all right. I know how much that is. I
Right.
get it.
100 billion billion. So,
I've seen it. Okay.
and I don't think it would be reasonable to be trying to find out the magic riffled
S-
list from
So we could pick
something
like
billion
maybe
billion,
like
right?
up to 1 million. How about
Yeah,
like
we'll time these
between?
up to a million.
Yeah, we'll see what we can get because I would think it would be interesting.
Yeah. So we did this last week. I'm creating a discrete plot of the timing of this function. We have to say first, just so we just get the timing, not the output of the function. If we look in the documentation, it says that it returns a list of the absolute number of seconds in real time that have elapsed together with the result obtained. We just want the absolute, the absolute time in seconds. Yep. Mm. So we want this for n going up to 10 to the 6, 1 million, we said. Let's do it in increments of 100 for now, just so it doesn't take forever. Oh, my bad. It needs to go from 1 to 10 to the 6. Yeah, it might still take forever. We're evaluating 10,000 different instantiations of this function. I'll give it a couple seconds.
Okay. So something we could try, and this
Yeah.
might be like something like to look into is we could try storing. We could try just instead of calculating the integer length name every time or the integer length every time, we could just store, 1 through 9,
Mhm.
how many characters 100, how many characters 1,000. Like we could just store them and then go from there. But
Right.
I don't know if that'd be reasonable. See, it's only a thought.
Yeah, so we could define some sort of recursive function which finds the number of letters in it, maybe, or maybe it wouldn't even need to be recursive. We remember we learned a couple times ago, this was new to both of us, that you can say f of n equals f of n equals. And what that was saying was it uses its defined definition if it remembers one, otherwise it finds a new one. And so that's really useful for recursive functions, which need to call the same function over and over and over again. And like you said, if we stored, if this basically does that job of storing the function each time, and it could kind of remember what it had previously done. So yeah, I think that would probably be a speed up. But this is still running, so I'm not able to do much. I'm gonna have to kill it. Let's try doing this every 10,000. So it's not super enlightening, but we'll do it for both. So magic and magic 2, we'll see what we learn. Ooh, yeah, it looks like magic 2 is doing it much quicker. I'm somewhat surprised that we're seeing larger times for smaller integers here. But it seems like they're all still considerably smaller than the magic function. So what's going on is magic 2 is using the fixed point list function, and magic itself is using nest while list. That's the main difference between the two. So it seems like fixed point list is doing a better job. And I would guess that this has to do with less calls to the integer name function. Up here in the nest while list function, we had to call the integer name function, I believe, 3 times for every value in that list. That's at least the way that I wrote it. I don't know if that was necessary, but that's probably what's taking the most time. And as we can see down here, in the fixed point list, it only calls integer name once for each time. This is just the first number. And then for every number, it only calls it once on itself. So I think that's probably why using fixed point list is considerably quicker in this case.
So yeah, the fixed point list, when it does a check and it just checks if the actual like output is identical, which I assume is the triple equal as opposed to the double equal. I don't know if there's more rigorous checks when it comes to these like equivalencies. So like if you use triple equal, that's checking if like the literal,
Yeah, so triple
definition
equal
of
is
it.
shorthand for same queue. And same queue returns true if they're identical, it's false otherwise. And as we can see in the documentation, for example, x is same with y is false, whereas x equals y remains symbolic. And then later we could say x is 2 and y is 5, and it would say false. But if they were
So
both 2, it would be true.
so would it be faster if was it faster to use to keep the function symbolic, or would it be faster to use the not in this case, but just in general?
Um,
You
so
can't really
using
keep this.
unsame queue here?
I mean, I don't know. I was just curious. Yeah, unsame queue. Oh, okay. I didn't know. This is
Yes.
this is the inverse of it.
Right. This is
Oh, okay.
basically the inverse of same queue. There's probably some minutia that's slightly different, which is why it required its own name. But yeah, it yields true if they're not identical, false otherwise. I don't think
Okay.
it matters too much for our
I don't think it's
application.
gonna do anything here, but
Yeah, mostly just because
theoretically, it
it's
should be.
actually comparing them each time. There is no symbolic.
Yeah, yeah,
Yeah,
I get
it's
what you're
taken.
saying. It's still the other one still takes longer.
Yeah,
Hmm. Okay.
about 3 times quicker to use riffle. And again, I'm guessing that that's all based off of the number of times that you call this integer name. Doing it 3 times, as it is here, is about 3 times slower than doing it just once in here.
Okay. Hmm. I see. Is there any, so you think there's anything else we could do to save time? We've kind of gone through most of the problem,
Hmm.
and we've gone through most of our hour, but I figure we can wrap it up and be like, is there anything we could do
to do this even faster. Looking at some of the other solutions, a lot of them can go a lot higher, but that's
Mm.
because they are storing, they pull like a list offline of like all numbers, like all digits available.
Oh, jeez. What? That's disgusting.
Yeah, so they pull like a, now that is being said, a lot of them are just basing it off Wikipedia, and I'm pretty sure you could
Uh-huh.
just call the Wikipedia thing and it would give you the list from the Wikipedia article.
Right.
So
Um,
theoretically, we could do it in less. We wouldn't actually have to type it out. We could just do a call to the Wikipedia article because we have that functionality, or at least the
mhm.
Wolfram Alpha has the functionality to look it up.
Yeah, yeah.
Wikipedia data, that's the function. So
Yeah,
you,
true. So what they're kind of missing in their implementation here is they're literally copy and pasting from some Wikipedia article. We'll pull up Wikipedia article, names of large numbers. There you have it. There's some list of names
it's
of
a
large
name of
numbers.
very large numbers. I mean,
Yeah,
yeah,
yeah.
it's where it comes from. I just thought it'd be cool to show off.
Yeah, if we could actually just get that in Mathematica without copy pasting. Let's see. And we can just say the name of the article. Cool. Without even doing the link, we can say names of large numbers. Let's see what that would give us. We might have to request a specific property. Yeah, this is just going to give the plain text.
Ouch. Can we get a table?
Yeah, that's because that's what we're looking for, right? We're looking for this table.
Yeah, I thought you could get that, but yeah, I'm not entirely sure like what, what this function does. So
Yeah, as we can see here. Whoa.
we're getting a lot.
This might even be kind of the input data to Wikipedia. It's kind of what's going on behind the scenes.
Yeah, I see. Well, um, what properties can we pull out? Can we see the elements? Do the elements call?
That's a good question. A list of possible elements. I don't think so. That might be for import only.
No, you have to put it outside of it, I think. Maybe? I don't know.
Let's try. This is all the links, rules, categories, languages, translations. Ooh, wow.
Geoposition,
Geolanguage.
where is the article written? Interesting. Well, this may
That's
be this may have been a fool's errand. Um,
coordinates not found.
numbers are not located on Earth. I see. Okay.
Mhm.
Well, maybe a fool's errand. I just thought it was kind of interesting. Most of these come from just a copy paste list of, you know, from this article.
Right.
So
Yeah. So if we could just get it straight
I
from the
was
article.
I was
Yeah.
hoping we could just I was hoping we could get it because we should be able like I wish you could just go through like each one and then read it. Like you can select parts of it. I know that,
Hmm.
but I'm not entirely sure. So,
Cool. Look, you can
well,
even create this big graph of. I assume this is how pages are connected. Graph
oh,
theory
it's
is
very
connected
interesting
to
looking.
binary tree, red black tree. That's pretty neat.
Well, okay, may have been a well, maybe there's something else to look at.
Hmm.
Um, well, may have been a fool's errand to look for this, but yeah, other languages go higher. But the Wolfram way the Wolfram way we did is totally programmatic. So it's requires minimal input. It probably, I think, I don't know where it ends. It probably goes up to like, 100 million. And it's like, let's stop.
Hmm.
But you know, we've gotten as much as we can. And I think, theoretically, this is as much as you really want to know.
Yeah.
Um,
Actually,
but
recreate this
we'll
graph
do it.
for our Wikipedia page. There it is. Okay. So this is how pages are linked together for names of large numbers. There's
There
some
you go.
pockets out here with shuffling and complexity. So some cool ways to access the data from Wikipedia, visualize how pages are connected, um, get different information from the web.
Yeah. All
Pretty neat.
right. Well, we've
And
approaching our hour mark.
yeah,
I think we've gotten a solution down.
we've got it. Yeah. Let's leave with a cool one. I wonder if we could find which one's the longest.
Guess we could just find the max. I don't know what the max cardinal is.
Yeah, let's see. I'm gonna do a table of a bunch of them. And then we'll find the largest by largest.
The longest list to get to
Take largest by. Ooh. So let's take the largest by string length. So these are just strings, and we want the largest string. If I spell string right,
there we go, string length.
get the 5 biggest. This might take some time, but with that, we'll give a quick recap. So we started with this problem of 4 is magic and trying to print out strings in this format of going through numbers, starting with an input and eventually getting to 4. And by taking the number of letters in the number name, and that's your next number. So 0 has 4 letters, 4 has 4 letters, so 4 is magic. 1 has 3 letters, 3 has 5 letters, etc. And we had some missteps, but we eventually found a pretty solid way to do it with some good help from the audience by using this fixed point list, which is a really neat function to create a list of all those numbers until they stop changing, which is at 4. 4 stops changing pretty much. Partition it, riffle it into the output that we want, capitalize and add a period, and that was our solution pretty much.
And there it is.
Ooh,
What? Oh,
that is my fault. What?
options instead of 5.
Oh, I forgot to use the word by. That is my big
Well, we'll
Curtis
run a little
by.
shorter.
Yeah. Do you have anything you wanted to wrap up with there?
No, I think that's really interesting. If you guys, if anyone has an idea, and anyone can come up with a way to, get that list of really big numbers, maybe use the Wolfram's knowledge base, it might be stored there, or using or scraping from Wikipedia. Feel free to, chime in and put something up. And Kevin will put this on Rosetta Code
Right?
and keep solving them. If you find, one day we'll run out of problems. Doesn't seem we'll do it anytime soon, but after that, if there are problems or explorations that anyone feels that we be worth exploring, maybe for a new coder to Wolfram or just a new coder in general to programming, send it our way. We'll do our best to get on that.
Yeah. Thanks everyone for watching. We found the largest one up to 1,000 is 378, so that's pretty neat. I wonder if there's any that get stuck in almost loops. It seems kind of close to the Collatz conjecture, the 3n+1 problem. But
Oh, that's true.
yeah, there's a lot going on here. So this was a lot of fun. Thanks everyone for watching.